Another number for you, Brady.
That's what I'm here for.
I'm loving this number. This number is great. It's so cool. 1, 4, 2, 8, 5, 7. I want you to just give me a number.
13.
Okay, fine. 13. I'm going to multiply this by 13, okay? Okay, I can't do that in my head. So let's... Now I take the last there's 6 numbers here, right? I'm going to take the last 6 of these, and I'm going to add it to the first one. That's 1 plus 8, 5, 7, 1, 4, 1. Now I can do that. That is 8, 5, 7, 1, 4, 2. Which, if you look carefully, is a permutation of this guy. So it's 1, 4, 2, 8, 5, 7. Give me another number, Brady. Give me another number.
112.
Right, 112. Very good. So 1, 4, 2, 8, 5, 7 times 112 equals. Right, let's do it. Okay, I noticed something about 112. You're a pain for choosing 112, but we see something else. Okay, 112, I think, must be a multiple of 7. In fact, it is. Right, you ruined it with it.
What, the multiples of 7 bring this?
Multiples of 7 are the only ones. If they do something else, they do something. So let's run with it. Let's run with it. Okay, multiples of 7. We'll do it. We'll take the last 6. Okay, 15 plus 999,984 equals 999,999. Okay, we'll do one more. Okay,
18.
18. Okay, not a multiple of 7. Thank you. 2,571,426. Do the same thing. Take the last 6, and I get 571,428, which is 1,42857. If I take anything that's not a multiple of 7, anything that's not a multiple of 7, and I multiply this number by it, and then I do this procedure of sort of taking the last 6 and adding the previous one, or the other ones, I always get a permutation of 142,857. In particular, if I take the numbers 1 to 6, there's 6 digits here, and I multiply this by them, I will always get a permutation of 157. So for example, obviously, if I multiply it by 1, I get 142,857, that's trivial. If I multiply it by 2, I get 285,714, which again is a permutation. Multiply it by 3, I get 428,571, and so on and so forth. And I can keep doing this. And if you go above 7, then you need to do this business of sort of taking the last 6 and then adding it. But you always get this this cyclic structure. This is an example of a cyclic number, in fact.
They're common.
Right, not particularly. Okay, so this is the only one that doesn't begin in 0. The next one, actually, after this one, is 058823529411767. This is another cyclic number. Okay, this has got 16 digits. You play the same game. You can take in this now. You would multiply it between. What's important is the fact it's got 16 digits. So if you do multiples of 17, this goes wrong. But if you do 1 to 16, you'll get a permutation of it, and then you can play this game as well, but with 16 rather than 6 digits. So here's the other weird thing about it. If you multiply it by any multiple of 7, you always get these all the 9s. If I multiply this guy, this has got 16 digits. If I multiply this by 17, I'll get all the 9s. Why does it work? Okay, let's see why it works. I'm going to need more paper.
No.
Okay, well, the important thing about that number, that 142,857, is it appears in the decimalization of a 7th. Okay, if I take a 7th, right, then a 7th is equal to 0.142857, 142,857, and so on. Keeps repeating. And this is critical. Why is this critical? Well, now think what happens when I multiply this by 10. I multiply it by 10, 10 sevenths. If I multiply it by 10, all these numbers just shift along 1, right? And now, but what do you know about this? This is just 10 sevenths is 1 plus 3 sevenths, right? Okay, so from this you can infer that 3 sevenths is equal to 0.428571. And the point is you can see that the multiplying by 10 just shifted everything along 1. Okay, and then we pull off this original one, but it got replaced by another one and getting shifted along. And then you're left with a permutation. It works perfectly. And it keeps working. Now we can do the next one, say, multiply it by 10 again. So do multiply it by 10, do 37s, and I get, again, I just shift, everything just gets shifted along by 1. But this, I know, is 4 plus 2 sevenths. So I get rid of the 4s, and I conclude that 2 sevenths is just 0.285714. And again, it was just everything got shifted by 1, but because it was the stuff that you removed that replaces it, you just end up with permutations. And that's why it works. That's essentially the essence of why it works. And actually, from this structure, you can see why, what the structure of all these cyclic numbers has to be. So you take a prime number, you take its reciprocal, 1 over a prime. Okay? It doesn't work for all prime numbers, but for some prime numbers it does. Actually, we'll come back to that in a minute. But you'll get something 0 times your cyclic number, and your cyclic number gets repeated, okay? This is a p minus 1, a number of length p minus 1. So here it was a 7th, and this blocks had a length of 6. Okay? So if I multiply this by 10 to the power p minus 1, in this case by 10 to the 6, I get 10 to the p minus 1 over p is equal to, well, my cyclic number, my cyclic number. So you get the same thing. Now you take these two away from one another, and you conclude that your cyclic number is equal to 10 to the p minus 1 minus 1 over p. And this is where those 9s appear. Okay, because if I multiply this by p, the prime number, which in this case was 7, or any multiple of 7, I get something that's related to the 9s, right? Because it's 10 to the some power minus 1, which is going to be all the 9s. Right, so that's why it works. All the cyclic numbers have this form. Not all prime numbers will give a cyclic number when you construct this guy. So the prime numbers that work, that give you, if you construct this, that will give you a cyclic number, are p equals 7, 17, 19, 23, 29. They're the first few, there's more, okay?
Are there an infinite number?
There are an infinite number, yes. In fact, and this is one of these things that I just think, number theorists, how do they dream up these things? We even know what percentage of prime numbers give cyclic numbers when you construct this. It's 37.395% roughly of prime numbers will give cyclic numbers in this way. I mean, why? We saw how if we multiply it by multiples of 7 and then we do our little construction that we discussed, that we get back all the 9s, okay? All the 9s appears everywhere in this. What else can you do? Let's look at it. 1, 4, 2, 8, 5, 7. Okay, let me take the first two numbers. Let me take the next two, 28. Let me take the next one, 57. I'll add them all together. Look what I get. Have some of that. All the 9s, right? Let me do this. Let me take 3. 142 plus 857. I add them together. What do I get? 999. Right? Let me even do this. Let me do 4, right? I get 1428 plus 5714, and I have to use every number the same number of times. 2857. What's that? 9, 9, 9, 9. That's amazing. It's amazing. I just love it. What is going on? It's all related, of course, to this very special property that it's basically these numbers can be written as 10 to some power minus 1 divided by the prime number. But it's clearly just, so it's all built in there. And they all have this property. They'll all do this. You can also work in different bases. You can have cyclic numbers in different bases. What happens then is the cyclic numbers, instead of being, we're working in base 10 as we're familiar with, but you just change this number from 10, and then you get the cyclic numbers again. Like you can play the same games, but of course they're cyclic in that particular base. And instead of getting all the 9s, you might get all the 3s or all the 4s, depending on whatever base you're in. It's amazing, but it doesn't even stop there. There's one more quirkiness that I've got to show you. 142857. Okay, now we're going to take the first three numbers, 142. We're going to square it to 857 squared. What do we get? 714285. What's that? it's another permutation of our 1, 4, 2, 8, 5, 7. It's amazing. And this number, actually, we're not the only people to have noticed that this number has sort of quirky qualities. There's something called an Enneagram. Now, this is some crazy Armenian spiritual leader from like wartime called Gurdjieff, and he basically was able to explain everything in life and the cosmos through this number. It's total nonsense. The less said, the better. But he did draw a nice, pretty picture, which I think we can draw, which sort of just gives us our last little thing to do with this nice number. So here we go. I draw that is a rubbish circle, but it'll do. We just draw 9 up there. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we're going to multiples of 3. We're not interested in. Boring. Get rid of them. Not that any numbers are boring, obviously. But and we just draw a triangle. Okay. Now the remaining numbers, we just sort of draw this nice pretty picture through them. 1 to 4 to 2 to 8 to 5 to 7 and then back to 1 again. And this is called an Enneagram. And apparently the properties of this can be related to cells and all sorts, but less said about the better, but it's a nice picture, isn't it? So 1, 4, 2, 8, 5, 7, cycle number, amazing, I love it.